Hi everyone, and welcome to the third session of the ENGR 315 lab tutorials. Today we'll be going over first and second order systems and seeing their responses to a step input. The way that this lab is going to work is that I'm going to go over the background and the Simulink scripts, run the simulation, save the results as a .mat file, and in your classes you will be provided with the result files. You will load them in your MATLAB workspace and carry out a number of tasks. So let's jump right into it. So the first exercise in this lab is the bump test. The bump test is basically a simple test based on the step response of a stable system. A step input is given to the system and its response is recorded. As an example, consider a first order system given by the following transfer function with the parameters k and tau, which represent the constants of this transfer function and adjust the behavior of the system. The bump test for this model looks something like this in the figure on the right, where the figure below shows the input step function applied to the system and the figure above is the response of the system. As you can see, when the step function is applied, the output reacts to it and tries to follow it until eventually settling at a steady state value YSS. Depending on the parameters k and tau, the behavior of the system can change. But why is the bump test useful at all? A utility of the bump test is to measure the k and tau variables and therefore estimate a transfer function for our system. Next, we need to see what these two parameters represent. K is the steady state gain of the system, which is defined as the amplitude ratio of the steady state output to the steady state input. If we go back to our first order model, we can verify the definition using the final value theorem. The time constant tau is defined as the time it takes for the system to respond to the application of a step input to reach 63.2% of its steady state value. Going back to the cube servo system, the S-domain representation of a step input voltage with a time delay of T0 is given by this equation, where AV is the amplitude of the step and T0 defines the delay of the step input. The voltage to speed transfer function can be approximated by first order transfer function, K over tau S plus 1, where K is the model steady state gain, tau is the model time constant. Now if we incorporate the input voltage into this transfer function and allow for the delay, we can write the frequency domain representation of the angular velocity omega m. Also, we can take the Laplace inverse of this equation and derive the time domain representation of the angular velocity. So the Simulink model that we have applies a step voltage of 2 volts with the step block here. You can see that step time is 1. The step time represents when the step function is applied. So for 1 second through the simulation, the value of the step function is 0, and after the 1 second, a step function with a value of 2 will be applied. And from the other end, we'll be reading the servo angular velocity in this scope. We'll use the speed readings then to estimate the parameters tau and k. The one more thing that I'm going to discuss is the simulation time, which I'm going to change to 2.5 seconds and hit run. So this is the velocity response to the step function for 2.5 seconds. I will save this output result and you will be provided with the corresponding .mat file in the lab so that you will be able to measure the k and tau variables yourself and estimate a transfer function accordingly. In the second exercise for this lab, we discuss second order systems and analyze the properties that affect their behavior. The second order system transfer function has the following form, where omega n is the natural frequency and zeta denotes the damping ratio. The properties of a second order system response depend on the parameters omega n and zeta. For an example, consider a second order system with the above equation subject to a step input of R naught over S, where R naught is 1.5. We can see the simulation results for this system on the right hand side, where the red trace is the output response YT and the blue trace is the step input RT. Now there are two important characteristics that we can define in this plot. The first one is overshoot, which measures the maximum amount of deviation of the system response from the reference step signal, and it is defined by this fraction, Y max minus R naught, which is our input signal, over our R naught. Another important characteristic is the peak time of the response, which depends on both the damping ratio and the natural frequency system, and it is defined as T max minus T naught, where T max is the time it takes for the system to reach its maximum value. For a second order system, the overshoot is only a function of the damping ratio zeta and follows the following equation. And the peak time depends on both the omega n and the zeta, and we have this equation to calculate it. Now let's see how the discussed definitions translate to the cube servo system that we have. From the bump test exercise, we know that the speed of the Quanzer servo can be modeled with a first order transfer function. We know that the position is a time integral of velocity. So by multiplying the voltage to speed transfer function by an integrator of 1 over s, we can derive the voltage to position transfer function. Now we can add a unity feedback signal to design a proportional controller so that the system tracks the reference position Rs. By incorporating the unity feedback signal to the model, we can derive the closed loop function, which is defined as g over g plus 1, where g is our open loop transfer function from the above equation. So here's the block diagram for lab 3B. The reference signal that we have here is a step function of 1 rad applied at time equals to 1 second. The block diagram is really similar to the bump test exercise, but with only two differences. First is that we don't have a transfer function to calculate the derivative because we're controlling the position. And second, the addition of the unity feedback signal, which is there to ensure that the reference position is tracked by the system. So I'm going to hit run. So this is the response of the system. As you can see, it can follow the reference position, which is equal to 1 rad, and the input signal looks like this. It goes to 0 after a while, and between 1 and 1.5 seconds tries to adjust the position of the cube servo. The output scopes will be available for you as a .mat file, so you can measure the percent overshoot and the peak time for this simulation. And that concludes the video tutorial for this lab. Thanks for watching. See you in the next one.